Hi there, guys. Thanks for coming back. Okay, I'm going to attempt to go through the first 5 questions in the first exercise of the Oxford HLAA course in mathematics. Okay, now the first exercise, basically, we're going to go straight into the questions, and there is some assumed knowledge beforehand. So there's some discussion here. I mean, look what it's called. It's called sequences, series, and sigma notation. There's a few investigations here in the book, which I'm going to skip past. There's a little talk about what a discussion about what a sequence is, and a sequence is sometimes called a progression. We're going to start off by dealing with a whole mixture of sequences, in fact. And obviously, sequences have terms. You should know all of these things already. So there'll be the first term, the second term, the third term. If we sum together a sequence, it's called a series, but we'll deal with that in a bit. Sequences, they say, can be finite or they can be infinite. Okay, so they can stop or they can carry on forever, of course. And they talk about examples. Here's an example of a harmonic series. Either way, we're going to get just stuck straight into these questions here. And I'm going to get rid of me because I'm a bit of a distraction to myself. I'm going to get rid of this little bit here. And let's just take the first example off here. Okay, and let's go through A, B, C, and D for question 1. Okay, so for each of these following sequences, write the next 3 terms and find the general term. So find the general term, what they mean is essentially find a formula for this sequence. That kind of means that you need to have some knowledge from before. So for example, this first one you might recognize as an arithmetic sequence. So for example, maybe the 5 times table, 5, 10, 15, 20, and so on. That's an arithmetic sequence or an arithmetic progression. Okay, it goes up in by the same amount each time. So we're constantly adding on, in this case, plus 5 each time as you go from one term to the next term. Okay, so let's just take all that stuff back there. Now, these sequences will start with a first term, let's call a first term A, and the second term will be A plus A common difference, okay, because we are adding on the same difference each time. If we add on another difference each time, we'll be adding on 2D from the original one. Add another D, then we'll get to A plus 2 lots of D now. Okay, if we add another D, you'll end up with A plus 3 lots of D. Now, the term number, let's just squeeze this in at the top. We've got n is 1, n is 2, n is 3. This is going to be the 4th term. So in our case, let's just take these things down here as well. In our case, for that first one, we've got 2, 7, 12, and 17. And so our A is equal to 2. And A plus D is equal to 7, so you can see that the common difference is 5, pretty simply. Okay, but what I was going to do here is just write down the nth term in this case, so I could go continue with this pattern. But you can see that for the nth term, we'd have A plus, well, here we have 3 lots of the common difference. Here we have 2 lots of the common difference. And you can see that 3 lots relates to the 4 by being 1 less. So we'll have n minus 1, let's put that in, n minus 1 lots of the common difference there. So this is your general formula for an arithmetic sequence. Now, lots of people will have done that before, so you can kind of skip through this one, and you might know this already. You might know this in a different way. You might just say, I know that this is 5n because it goes up in 5s, and I know that the first term is 3 less than 5. So take away 3 to get down to the 2 there. Okay, or some people might know the minus 3 from the 0 term. So the 0 term here is if I take off 5, if I keep going backwards, I'll get back to a minus 3. Some people call that the 0 term, which is what they're adding on at the end. Either way, whatever system you've got, you should be able to understand that's pretty straightforward. I would use this formula up here, though, for this, which can also be written as U1, i.e. the first term being U1, and this is our sequence UN. Okay, so we would have U1, U2, U3, U4, and so on. This would be U4, the fourth term in the sequence of U. We could call the sequence something else. We don't have to necessarily call it U, we could call it R. But R is often used for a common ratio later on. So U is a letter which isn't used for much. So they choose to use that for these sequences. Okay, so U1 plus N minus 1D, that's another way of writing UN equal to this thing here. So there's a sort of general formula for the first one. Okay, so what I would do for this first one, next three terms are dead simple, just keep adding 5, of course. But then I would use this thing here. So I would say U1 is 2, this, then plus N minus 1, N minus 1, we don't know what N is, so we're finding the general term, so N is involved, so it's for any term, and then I'm going to put D in, D is equal to 5, I'm going to put times by 5 at the end there, because you don't normally put, leave out the times if you're just putting a number on at the end of a bracket. You would if you put it at the front of a bracket, but not at the end. Which kind of makes this formula a bit strange, to be honest, because normally you put the D at the front. Okay, then so this is our UN is equal to this, and then if we multiply out those brackets and add on the 2, so 2 plus 5n minus 5 is going to give you 5n minus 3, which is probably what you've got already. Okay, let's get rid of all of that stuff. Okay, so there's the first one. That's basically stuff that you've seen before, so I'm not going to spend too much time in that. Right, this second one. This is a geometric sequence. It's geometric because as you go from 2 to 6 to 12 to 20, am I right there? Oh, let's have a look here. Maybe it's not geometric. I was thinking it was times by 3. Oh, it's not geometric. Let's have a look at what it is then. Let's look at the common differences here. The common difference there is 4. Common difference there is 6. Oh, common difference there is 8. Ah, okay. So I thought this one might be geometric. In fact, it's not. So geometric would mean it would be timesing by a common ratio each time. So times by 3, times by 3, times by 3. Because the number is changing each time here, it's not a geometric sequence. Now, some people might recognize this one already. So say, for example, I had the numbers 1, 4, 9, 16, and so on. You might recognize this as these as the square numbers, of course. Then if you look at the differences there, we've got 3, 5, 7. And as soon as we get to a second line of differences, our first differences being a linear sequence, then that tells us that the top line is a quadratic sequence. And that's what we're getting in this case here. Okay, now this one is going up, the second difference is going up in 2s, and the second difference is going up in 2s here as well, which means that this is related to x squared and not 2 lots of x squared. If we had 2 lots of x squared, all of our second differences would be double. We'd have here 4 instead of 2. So I know that this sequence here has got something to do with x squared or n squared in our case. So what I'm going to do is I'm going to extract from these numbers 2, 6, 12, and 20. Now I'm going to extract from that n squared. So this is my UN, if you like. I'll put n at the top. I'm always forgetting a little bit here. 1, 2, 3, 4, just the term number. And I'm going to put in here n squared. So n squared is 1, 4, 9, and 16. And I'm going to extract those numbers because I know that this is a quadratic sequence. If I extract those numbers from the sequence, I'm left with 1, 2, 3, and 4. Now this is a linear sequence, and in fact, it's the linear sequence which is at the top. It's just n. Okay, so what I've done is I've taken this line away from this line, and I've ended up with this line here. I knew to take away n squared because I saw that the second difference of this sequence was 2, just like the sequence of n squared. So I knew this had something to do with the quadratic sequence. So I took away the n squared. Okay, I've taken away the n squared, and now I realize that my formula un is comprised of both n squared and n. Okay, or in other words, it's n times n plus 1. If we have a look at testing this, for example, let's take the fifth one. Let's do U5. We've got 5 times 5 plus 1. It's going to give us 30, and we're expecting 30 to turn up to the next in the next one. So we've added 4, added 6, added 8, added 10 to get to the next one. So we're happy that that one's right. Okay, let's just get rid of all that. By the way, if you want to just stop the video and just try and get the answers to the next ones, by all means you can do. I suggest that's a good idea, in fact. But let me just go through the next ones. I'm not going to stop myself. So for the next one, we can see that we have a sequence on the top of the fraction and a sequence on the bottom of the fraction. So we can see it's going 1/2, 2/3, 3/4, 4/5, and the next one's going to be 5/6. Okay, so I can see that. Let's write down n again. We've got n is 1, 2, 3, 4. And I've got 1/2 there, 2/3, 3/4, and 4/5. Okay, that's my un. And you can see that my nth term, the top number is exactly the same as n. So I'm just going to put n as my numerator. And my denominator is 1 more than that. So it is legitimate to split your formula into a fraction, just like the fractions which are occurring here. So these sequences, the sequence is generated by the numerator and the denominator having a different formula for it. And you can just write it as this thing here. So that's your nth term. That's the general term. You can say un in this case is n divided by n plus 1. Okay, the final one, we've got this one here, and I think this is a geometric sequence because it's being times by 2 each time. Okay, right. So for this one, we can see it's timesing by 2. Geometric sequences start with a first term, let's call it a, and the next term we'll times by something to get to it. Let's call that r for the common ratio. So the next one's going to be ar squared. So what we're doing there in each case is we are timesing by r to get to the next one. And that's exactly what is happening with this. So this was our first term, second and third. Here's n. You can see how the 2 relates to the 3 there. The 1 relates to the 2 here as well. And essentially we have an r to the power of 0 there. In other words, take a 1 off the 1 itself there. Take that off. Of course, r to the power of 0 is equal to 1. Okay, so in our nth term here, we can write this as ar n minus 1. So that's the pattern which we're following. Okay, so that's the geometric sequence. I mean, these will turn up later in later exercises, these common formulas, but it's nice to be aware of them early on. So the formula for this one is simply 5 multiplied by r. So r is 2. Divided by 20 is 2, as is 20 divided by 2, and so on. In fact, any un divided by the previous one always gives you 2 in this case. Okay, so here we've got 5 times by 2 to the power of n minus 1. Yeah, we can leave it like that. Some people now, just like your calculators, might leave that as 5 dot n minus 1, where the dot is representing at times. Would be legitimate. That's what you see on your calculator, but I mean, I would stick with this still. Okay, you can obviously test this one out. Feel free to do that. Right, let's have a look at the next one. I feel like I'm spending way too much time on this. Okay, question 2. By the way, if you just want to skip forward in the video, if you find things easy, then by all means, skip forward. Okay. Okay, let's just look at the answers to this one. Here we go. There's 5r minus 3 for the first one. Well, they've used r and not n. But that's okay. They've just said r is any term, and n can often be written as the last term instead. Here they've used r as the any term, if you like. Okay. Right. So let's have a look at example number 2. Okay, let's take this one here. Now you can also already see some sort of strange things going on here. We've got these curly brackets, and they say you are, not UN, so I'll stick with their notation. We've got these curly brackets. Now the curly brackets define sets. So for example, again, you've probably seen this before. Oh, sorry. Something like this. I'm really struggling with that. Okay, 1, 2, 3. This is the set of numbers 1, 2, and 3. Okay, it's just a set of things. They have put you are as a set of things here as well, and they're defining R be a member of the positive integers. Okay, so integers being 1, 2, 3, 4, 5. We should talk about that as well. Okay, so you don't really need these curly brackets, to be honest. It's fine just to write you are. They're just identifying this as a set of numbers that we're interested in. So you don't need the curly brackets in the second bit here that you can see as well. Okay, so this one is saying you are is equal to 5r minus 2. And the bit at the end, this thing here, says r belongs to, this e, you can read as an element of or belongs to. So this is an element of, and this z stands for integers. And there you can see that they've put a plus on the end, so they only are interested in the positive integers. What they mean is 1, 2, 3, 4, and so on, infinitely far on. You might be thinking that's a little bit strange. You might be thinking it's strange because why didn't they just call this the natural numbers? Okay, this doesn't say in, by the way. This says this is n. This is my attempt at doing a bold kind of double stroke n. Okay, which looks something like this when you see it in books, or maybe sometimes it looks like this. I don't think it does, to be honest. I think it normally has the n at the front, the double stroke at the front. This is difficult to do, though. Or sometimes you might see it as a bold n, but that's difficult to do. So we do this kind of double stroke. So this stands for n. This is natural numbers. And if we expand our system, so natural numbers are counting numbers, and debatably that includes 0. That's debatable. We'll look at that in a second. And then if we expand the system, we get to integers. Okay, and integers include negative numbers and 0. Yeah, and you might be thinking, well, why didn't they just say, let's call this the natural numbers? But they've specifically tried to say just the positive integers, so they don't want to include 0. And natural numbers ambiguously sometimes do include 0 and sometimes don't. So often you'll see things like n plus or n star, just to say all of the positive integers, not including 0. Or sometimes you'll see n0 or n0 like this. I think the 0 on the top, meaning it does include 0. Okay, anyway. So this is really just talking about using numbers 1, 2, 3, 4, 5, and so on. Okay. Right, let's put that back. Okay, so what does it say? It says write down the first 3 terms of the following sequences. Well, that's pretty easy. Put in 1, 2, and 3 in here. I'm not going to insult you on that one, okay? So for the second one, let's have a look at the second one. It's saying you are equals, and then we've got minus 1 to the power of r over r squared. And again, it's talking about r belonging to the positive integers. So if we put in 1, for example, you'll see that you'll get minus 1 to the power of 1, which is minus 1, divided by minus 1 squared, which is just 1, which gives us minus 1. Okay, so that's going to be u1. I should really do some working out for that, but I'm kind of running out of space. So let's just say u1 equals minus 1 to the power of 1 divided by 1 squared. And that gives us the answer of minus 1. Right, so u2 is equal to minus 1 squared, which is going to give us 1, positive 1. And then we're going to have, if we put 2 in on the bottom, we'll get 4 as well. So we're going to get 1/4. Now you might be able to see what's going to happen with these ones now. When you do minus 1 cubed, that will take you back to negative 1. You have minus 9th, u4 will be plus a 16th, and you can check with your calculator if you want. What's quite nice about this is you can see that the numbers are oscillating here between negatives and positives. And the reason why that is this part of the formula. And that's why they wanted to show you this really. If you put in a -1 to the power of odd and even numbers, it will give you, so this to the power of, say, an even number, and a natural number there, so 2n would be even. This would always be positive, and then when we do that to an odd number, let's call it 2n plus 1. Okay, so I know 5 times 2 plus 1 is 11. That's going to take you to a negative number again. So that's what they're talking about there. They're trying to get you to oscillate in these terms between positive and negative. Okay, I'm aware this is going on a little bit. Sorry about that. Typical. Okay, let's have a look at example number 3. Okay, example number 3. Write down the following sequences using the general term. Okay, well, you can hopefully see this. If you want to stop this video now, if you're annoyed at me droning on here, in fact, we can have a little sip of my cup of tea, which is already getting cold. So you can see the first one. If you want to have a go at this, have a go. I'm going to plow on. You can see that this one is going up in 3s. This is just an arithmetic sequence. So this is the 3 times table actually. So it's just 3n. Or general term, I think they're going with r. So we'll call that 3r. Let's call it u. That's pretty straightforward. I wouldn't overcomplicate that. And for the next one, you can see it's being times by 5 each time, and the first term is 2. So there we go. We've got the a times r to n minus 1. And that's what we're going to do here as well. Oh, but we have oscillating numbers here. So oscillating between positive and negative. So there's a couple of ways we could deal with that. We could put on the front of this -1, and then we could put that to the power of, say, let's just try and put that to the power of n and see what happens. Well, if we put it to the power of n, this will give us what we want. 2 times 5 to the 0 for the first term will give us 2. But then when we put 1 in here, this will give us a negative. -1 to the 1 is -1. And we don't want a negative there, so we're going to need to change this to either n minus 1 or n plus 1. Now that's a perfectly fine formula. However, you might be able to see an easier way of dealing with this one. In fact, you can see that you have a to the power of n times by b to the power of n there. So you've got this and this. You have that kind of form in this and this. So we can bring those together. That's a, b, power of n. So it's one of our laws of indices. So in other words, and you might have spotted this already, this is -5 to the power of n minus 1. Okay, now I am laboring this one, and I realize that because in truth, 5 wasn't the common ratio here. Right? -5 was the common ratio. So I could have made that much quicker. Apologies about that. I could have made it much quicker just simply by doing, if you remember, I was doing this before. If I did un divided by un minus 1, so any term divided by the previous term always gives us -5. So when we put in this, there we go, we've got 2 times -5 to the n minus 1. Apologies about being a little slow on that one. Okay, I was kind of just building it up. Okay, no excuses really. Okay, and for the last one, we've got C. We have a formula on the top and a formula on the bottom. And you can see we've got UN or UR, whatever you want to choose as your subscript. And with the top number is N, and the bottom number here is the 2 times table, 1 removed. So we've got the 2 times table in maths is 2N, and we want 1 higher than the 2 times table there, so 3, 5, 7, and 9. Now again, for those bottom numbers, you can obviously do 3, 5, 7, 9. You can put that into UN equals U1 plus -1D. That's the formula for an arithmetic sequence, remember, and that will give you this thing here. It's pretty simple here, so that's why I'm not laboring it. Okay, let's have a look at that. Not that. Let's look at this. Let's just see what they've done. Yeah, so you can see they're coming up here with the brackets, the curly brackets to denote sets. You don't necessarily need those. You can see what we've done in the second one, same as what we've got. Oh, and they've defined, interestingly, they've said where our numbers are starting with. What do I mean? I mean, R belongs, so that they've come up with a domain for R. So they've said R belongs to the positive integers, and I forgot to do that. So let's have a look at this one here, this second one, because actually that's kind of interesting again. They've come up with something slightly different there. Let's just steal that. Okay, so let's steal the second one. Now you can see that they've got here, for this one, they've defined R to be less than or equal to 4 when they put it in here. Let's test that one out. So it says 2 to the power of minus 5 to the power times by minus 5 to the power of R minus 1. And they say where, oh, okay, that's something I didn't notice. Okay, I messed up twice in that. I wonder if you can think why this is the case. R is less than or equal to 4. What the difference between this one in the middle is compared to the other ones. And I didn't notice this. But this one has a dot, 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 and this one doesn't. And this one does. Okay, so this one is finite, actually. Okay, so there's only actually 4 terms here. So the first term, pretty straightforward. When we put in 1, we'll get out the answer of 2. When we put in 2, we'll get out the answer of minus 10, and so on. So there's only the 4 terms there. And we've got to stop at 4. So they're telling us to stop at 4 here, but they're also saying R belongs to positive integers. Now they've made a bit of a meal of that, because really you could say R belongs to 1, 2, 3, and 4. I think that might be easier to write down. So that's the only valid set of numbers for R. There's only 4 terms, essentially. They've written it down as, let's take the positive integers, and we only can go up to 4. Okay, I was glad I checked that one. Okay, let's look at the next thing. We've got example 4 and example 5, and then there's the exercise. Well done for persisting. Okay, so let's take example 4. Example 4 in this case. For each of the following series, written in segment notation, write the first 5 terms. Okay, well, we need to know a little bit about sigma notation. And again, a lot of people will have met this before. So if you've met it before and it's obvious, you can have a go at these questions. Otherwise, you can just listen in. So this is basically telling us, sigma tells us to sum together the terms which are created if we put in this case, R is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so it's asking us to sum this sigma, capital sigma, so lowercase sigma is used for something else in mathematics, for standard deviation. But this is lowercase sigma, but this is the uppercase sigma. Sometimes you see it with little hooks on it as well. Okay, right. So it's like a massive kind of B. Right, when we put in R is equal to 1, we're going to get 1 times by 1 minus 1 there. That's the first term. Then we're going to need to add in 2 times by 2 minus 1. All I'm doing is substituting R into each of these and adding together each of those terms. Now, I can do dot, dot, and add these together as well. And the last term here should have left more space. It's going to be 10 times by, we can see one less than that, 10 times by 9 is going to be the last term you're adding on there. Now, if you're just evaluating this, you can do this on your calculator. Let's have a look online to this one. Let's go back. And let's go to Texas Instruments in there, because I know I can zoom on this. And let's just have a look over. Let's just hover over this for a second. So if you have a look on here, okay, this key here where my plus is hovering over, this key is what's, if you're on Scratchpad, this is going to give you your sigma notation. I think you can also do it through the menu option as well, but there's kind of shortcut keys, and this will give you a whole load of templates which you can do. And so you can set this one up and evaluate it on your calculator straight away. There are other ways of doing this. If you know well, there are other ways of doing it. I'm not going to go into it now. You can do these on your calculator. So you can do them longhand or you can do them on your calculator. Guys, I'm not going to do any more on this one. I'm aware that it's going on, but you can see how they're done here as well. And you can see they've used this little trick here. For this one, we've got -1 to the power of r times by r squared. And you can see that this one is going from is going to oscillate essentially. -1, 4, -9, +16, -25. Now, actually, they only want you to write the first 5 terms. They don't want you to evaluate them. In fact, this part B here, you can't actually evaluate because it's the sum to infinity. And since each of those terms gets larger each time, the whole thing is going to oscillate between positive and negative in that case. And the numbers are going to get larger in magnitude as well. So for part B, yeah, you can't evaluate that at all. For part C, you can see what they've done. They're simply substituting in 1, and they're continuing in this case up to the 5th term. So substituting in, for example, let's check that one out again. Sorry, it's turned off. Okay, so let's just look at this one here. So this one is saying the sum from r is equal to 1 to infinity, although they only want the first 5 terms, to r minus 1 and r plus 1. Well, again, you're just going to substitute in. So when we substitute r as in 1 in there, you'll get 2 times 1 minus 1. I think that's pretty clear. Okay. Right, that's me saying I think it's clear. You may beg to differ. But I guess if I'm saying something's pretty clear, then I'm expecting for the students who are taking this course for it to be fairly obvious. I'm expecting your maths to be at a reasonable level already. Okay, next little bit. So question 5, we're nearly there on this one. We've got first term is, write each of the following series in sigma notation. Okay, so first one is going to be 3, 11, 19. I can see that's going up in 8s. In fact, this is 3 plus n minus 1 times by 8, which if you simplify it, that's going to give you 3n minus 5. In fact, you might see these as 5 less than the 8 times table. Okay, so this is, video is clearly going on for too long. 8n, sorry, take away 5. Okay, that's just me expanding this. Shows I shouldn't skip steps. Okay, giving us this here. So what we want to do in our sigma notation to sum this, to sum 5 terms here, we can say r is equal to 1 to 5 in 8r minus 5. Now we need to be consistent in the use of r and r there. If you wanted, I could have called this n and n. That would have been fine as well. In fact, this is a dummy variable in this case. So if you wanted to call this thing I instead, it doesn't really matter. The sum is still going to be the same. It doesn't matter that it's called n or r or whatever. It's just a dummy variable. Okay. So anyway, that's the sigma notation for the first one. Clear that one out. And for the second one, now this is carrying on forever. I spotted that this time. So we need the sum from, let's call it I this time. I is 1 to infinity. And because this is oscillating between positives and negatives, I know I'm going to need to use that trick. -1 to the power of I. Now I just need to think, if I put in 1, am I going to get a positive answer for my first term or a negative answer? So when I put in 1, I can see I get -1. to the power of 1 gives us -1. And I want a positive answer here. So I'm just going to shift that off by 1. Let me put +1 in, although I could equally put -1 there. And now I can see that when I put in 1, I'll end up with a squared, and that will give me -1 squared, which will give me 1. And then when I put in 2, I'll get cubed here, and cubing will give me -1 cubed, which will bring me back to -1. Okay, so I need to push it off by 1 here, and I can do that by adding 1 or minus 1. Okay, so that's the answer to that one. I suppose it wouldn't really matter here if I started with, if I left that as I could start with 2 instead. Okay, that would be valid as well. I don't have to start at 1. Now, that also works. And because there are infinitely many terms, from 2 to infinity, this still gives us an infinite amount of terms. Okay. In fact, that trick could have been used for the first one. Let's just go back to this. There were alternative answers to this first one. Because although we had, let's say, what was it, 8r minus 5. And to get the first term, we could have put in r is equal to 1 and go up to 5. Okay, so that gave us a first term when we put in 1, gave us the 3. Now, if instead, let me think about this. If I wanted to start at 2 here, instead, I'd need to go up to 6 to have 5 terms. But I'd have to adjust my formula. That will still go up in 8s because I can see I've got 8r here, but I'll need to adjust the -5 because it now won't start at 3. So if I put 2 in here, I get 16. To take us back to 3, I'll need to take away 13. So this will need to be take away 13. This is also an equivalent other answer to whatever the book's going to give you for this one, probably the first one I gave you. So you can play around with that. There are infinitely many answers which you could give in this case. Okay, let's have a look at this final one. We're almost there with this first exercise examples. So with this final one, we've got -6, 12, -24, 48, and so on. So we can see that we're timesing by -2 in each of these cases. If I take un and divide it by the previous term, it's always giving us -2. Okay, so I can see I'm starting at -6. That's my first term. I'm timesing by my common ratio of -2, n minus 1, or r minus 1. I'll use n in this case. Now, let's just put that in brackets. And I'm going to say that starts n is equal to 1, and it's going up to 6 terms. So n is 1 to 6. Phew, I think I'm done. So let's have a little look. What did they do there? Am I messing up with this one? What have they got there? Oh, that's interesting. They've done, oh, they've got this one wrong. Okay, let's have a little look at what they've got for this one. So you can see what I've got there. You can see that this is definitely a geometric sequence, and I've used the format of a geometric sequence there. But if you have a look at what they've done, so you see, it's always best to buy the book, because the book has an online version, and the online version has eradicated a lot of the mistakes. So if we have a look at the answer which they've given here, you can see that if we put in the summation of this, if I put in r is 1, I'd get out -6. Okay, so -1 to the 1 is -1 times by 6 times by 1 gives us 6. That will give me -6. And the next term, when I put in 2, I'd get +12, no problems. But then when I put in 3, I'd get 6 times 3 here, which would give me 18, as you well know. And the to the power of 3 minus 1 to the power of 3 will give us a minus there. You can see that's not what they've got here. But they've assumed that this is a sort of a corruption of an arithmetic sequence, whereas in fact it's not. It's a corruption of a geometric sequence instead. In fact, it just is a geometric sequence. Okay, so their answer is in fact wrong there. Right, good. Glad I spotted that. Okay, so just to have a look, exercise 1A, you've got 6 questions there. Again, got the answers in the back of the book to check, but the online version is much better. Obviously, get a copy of the book. Guys, thank you very much for listening. That's well done for getting this far. I'm exhausted. You probably are too. Now you've got to get on with the questions, and I'm going to shift on to the next exercise and make the next video. Okay, guys, thank you very much. See you later.